Hi, this is Atlas, and this is Understanding a Payload's Life, Part 2. We're going to continue with payload generation. So, popular frameworks like Metasploit use cell code. This is fully position-independent code, or a combination of that plus other things. Why they do that? Because of the flexibility of cell code. You can use it within exploits, post-exploitation tasks, and you can execute it from within a lot of executable recipients. So for example, Metasploit automates this in a way where you can set a different of settings or a configuration. You press generate, and then you have your shiny cell code, Meterpreter cell code. Okay. In this section, we are going to analyze first how to build static Meterpreter DLLs, and second, how those DLLs are manipulated to generate our final payloads. Starting with building Meterpreter. So we remember that this payload consists of multiple or a lot of reflective DLLs, mainly Met server in charge of communications and loading extensions, and the extensions, which are the extended API, standard API, Kiwi, Priv, and so on. When you install Metasploit, all these DLLs are going to be there, pre-compiled, and ready for use. Okay? But what happens if you want to compile them yourself or modify the source code and compile them? You have two options. The first one is via Visual Studio, a project, or the second one, main one, is Docker. Okay. The Metasploit payloads repository has a lot of documentation about this with all the steps. And well, you have an image of an example doing it through Docker, the Met server x64. And now we're going to see an example of doing it via Visual Studio. So note that what makes these DLLs reflective is just the result of building them with a portable reflective loader. If you go to the source code of Met server or any other extension, you will see include reflective DLL injection, blah, 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 reflective loader.c. Okay. And it's something like this. When you build those two things together, you get a reflective DLL with an exported function, which is essentially the loader. Okay. So before starting with the reflective DLL manipulation, we're going to see the building with Visual Studio. So here I'm going to git clone. Don't forget to use recurse. Now that we have it cloned, we can go to the folder, Meterpreter, source. No, not source. In the source, you have all the source code, of course. In the workspace, you have the Meterpreter Visual Studio solution. So we can open that. And we see all the extensions, all the DLLs here in different projects. So we can set release, for example, an x64 or whatever we want. And if we go to right-click build in Met server, it succeeds. We go to extended API, succeeds. We can do it for everything with build solution. And sometimes extensions like, I don't remember, Python, I think, they fail because there are some issues. I don't remember exactly which ones, but expect some problems for some of the extensions. So in the output folder, we can see those compiled DLLs right now. Okay. So reflective DLL manipulation. If we go and use these DLLs that we have just built and execute them like regular DLLs, we are not going to achieve anything. Okay. In order to initialize them properly, we need to, from memory, we need to call the reflective loader export directly. Okay. So note that reflective DLLs, as we mentioned, is just regular DLLs built with a portable reflective loader. So let's dissect. I should have tools, PEVer. Let's open this and let's go back to Metasploit, see Meterpreter, output, and MetServer. So we can check all the information in PEVer, but essentially if we go to file header, we can see this is a DLL. And if we go to the exports, which are essentially exported functions from this DLL. So when a program uses this DLL, or when a program uses a DLL or loads a DLL, the program is going to have all the functions, all the exported functions provided by the DLL available. Okay, so the exported function available from this MetServer DLL is this one, just one, which doesn't have a name right now, just the ordinal number one. This is the reflective loader function. Okay, and in order to initialize this DLL from memory, we need to find and execute this function. Okay. So in regards of the name, from Metasploit 6 onwards, it was removed, but traditionally it had reflective loader. But of course, it was an indicator of Meterpreter, so they removed it. So now, how does Metasploit do to convert metserver.dll to cell code? What it does is it patches a small piece of cell code or independent code into the DOS header of MetServer. This is typically called the bootstrap code or the initialization stop. Okay, and the main goal of this code is calling the reflective loader exported function. Something like this. We will have the bootstrap within the DOS header, and when we execute position 0 of this buffer or this code, we're going to execute the bootstrap. And the bootstrap is going to find and execute the reflective loader export. When this export is executed, the reflective loading process of the DLL is going to initialize. Right? So essentially, this piece of data, the bootstrap plus the reflective DLL, is now or can now be used as if it were a cell code, even if only the beginning of it is fully positionally independent code. This is the bootstrap source code in ASM. I am by no means an ASM expert, but I'm going to try to simplify it so you can understand the main things. So here highlighted, we can see, well, it first, the bootstrap first gets its current location, and then it executes the reflective loader function, the exported function. How does it do that? It does it because the bootstrap knows where the exported function is located. How does it know it? Because we know the size of the DLL and we know the size of the bootstrap. So here Metasploit calculates with the reflective loader offset where the exported function is located. And then it just sets this information. And when the bootstrap is executed, it goes straight forward to the reflective loader function. Okay. Here is also the code where the bootstrap is generated with the options. It's converted to cell code, it's assembled, and then it's patched within the DLL from position 0 to, well, the length of the bootstrap. Okay, so now I've generated a cell code, a Meterpreter stageless cell code called MSF.bin, and I'm going to download it and analyze it. Okay, I've downloaded it, msf.bin, and I'm going to open it with PVR. So I've never used the compare, but I feel it's going to be very useful for this. So if we click on the DOS header, we see, oh, Metserver. Hold on. I guess I don't really know how to open both. Well, it's okay. So Metserver, the DOS header, we see MC and at different dots. Then this program cannot be run in those mode, blah, blah. But if we go to the cell code, chun, we have the MC header, and that this program cannot be run in those mode. But there is also more data between those two things. Okay, you see. This is the bootstrap code we have patched, or Metasploit has patched. Okay. So now our Metserver DLL can be executed as cell code. Okay. But if you execute this cell code, you're not going to receive any Meterpreter session. Why is that? Because there's still the most important piece missing, the configuration settings, the L host, L port, extension settings, and so on. So Meterpreter has something called the configuration block for containing all these settings. Okay. When you generate a Meterpreter payload, this configuration block is created dynamically with all the things you have selected. And this configuration block is appended at the end of Metserver. So the result is something like this. We have the bootstrap, we have the rest of the DLL with the reflective loader export, and we have the configuration block with all the settings about the session settings and so on. So this is the source code in Metasploit. Stage Meterpreter is what we have seen in the other slides. Stage Meterpreter is in charge of getting the DLL with the bootstrap. Okay, so the DLL with the bootstrap, we append or prepend, we append the configuration block at the end. And the configuration block, you can see all the different options: architecture, exit function, expiration, transports, extensions, whether it is stagelet or not. Yeah, you already seen it, but MetServer, the original DLL, doesn't have anything below these sections, whereas the cell code has an overlay, which is essentially the configuration block. Okay. So now the configuration block structure, this is something that Metasploit documentation explains really nice with a lot of details. It essentially has one session configuration block, one or more transport configuration blocks, and one or more extension configuration blocks. I'm opening the link, and well, there's different explanation about each of the configuration block things, but at the end of the page, configuration block overview, we can see a summary of everything, and it looks like something like this: socket handle, the exit function, the expiration, UUID. Then we have information about the transports. Okay, it can be one or more transports: TCP, HTTP, HTTPS, and so on. For HTTP, we have proxy settings, user agent, and so on. And then we also have the extension settings, which can be one or more. This means that we can create a payload with MetServer, but which also contains the STD API embedded within this configuration block. So here it would be STD API size, the STD API contents, like the DLL. Then we have another extension, Kiwi, the size would be here, and then the entire DLL here. Okay? So, a final detail, which is really important. If you paid special attention when we were talking about the bootstrap, you probably noticed that it did more things than what we explained. Okay? Instead of just calling the reflective loader export, it does a second call to DLL main, passing a pointer to the configuration block. Okay, so the first thing, when it executes the reflective loader export, this is going to load MetServer in memory, but nothing else. The second call to DLL main with a configuration block pointer is what it's going to give us the Meterpreter session. Okay, so this is the same invoked MetServer code we saw in the previous slides. First, invoke reflective loader, we saw that. It calls the exported function. But then invoke DLL main each instance, DLL Metasploit attach, and a config pointer. So once again, we know the size of the DLL, we know the size of the configuration block, we know the size of the bootstrap, we know the size of everything. So we can inform the bootstrap where the configuration block is located, which is what Metasploit does here. So having the location, the bootstrap can then call DLL main with this reason DLL Metasploit attached, and with a pointer to the configuration block. And yeah, here I say met server DLL main, huh? Yeah, if we go to the reflective loader source code, we're going to see this. If this variable is not defined, reflective DLL injection custom DLL main, then we're going to use the original DLL main function of the reflective loader repository. So yeah, this DLL main is a regular one, nothing fancy. But when we go to met server, we are going to see the variable defined reflective DLL injection custom DLL main. And then met server defines its own DLL main with this instance, this case that we were talking about, DLL Metasploit attach, which gets the pointer to the configuration block and initialize everything. So it calls init with the pointer, and then within init we see server setup with the configuration, and it starts everything and setups everything. So if we execute this with the bootstrap, with the configuration block and everything, if this cell code is executed, we're going to receive the session. Nice. So as a bonus, Metasploit modules. So we have seen how met server and the different extensions are executed using reflective DLL injection. Okay, but of course, Metasploit has a lot of exploits and modules that also use reflective DLL injection. So this framework typically does or do two approaches. If the exploit or the module is more or less, it's not very complex, the exploit or the module will typically use C code and Railgun, which is a component within Meterpreter that allows the execution of WinAPI functions like dynamically. And it's awesome, but it's something for another video. But for complex stuff, it typically uses reflective DLLs. Okay. So both techniques can run exploits and different things within the current process, but the good thing or the benefit from reflective DLLs is that they can be injected into remote processes, and if something goes wrong in those processes, your original session keeps living. Okay. So as an example, the Juicy Potato module. This is a precompiled reflective DLL, which is injected into a remote process to escalate privileges from a service account to system. So what we see here in the code is library path. It finds the precompiled DLL on disk, okay, on the Metasploit folder. Then we see how inject DLL into process. It injects the Juicy Potato reflective DLL into a remote process and gets the offset to the reflective loader function, because here we are not using any bootstrap. So the code itself saves this location for later use. We then have all the configuration settings and the payload, the encoded payload. And this is injected into the remote process. Okay? Inject into process, the remote process, and the configuration, which contains all the configuration settings and the payload. And this is payload memory. And finally, we're going to execute everything by creating a new remote thread, which points to the reflective loader export. This is the exploit mem plus the reflective loader export. And then we are going to pass the settings and the payload as an argument. And this will work. Okay. Nice. So this is how Metasploit does everything in terms of payload generation. But what other frameworks do that is different from Metasploit and is interesting for us? So other frameworks like Sliver, Havoc, Mythic, or Covenant have builders or compilers within their automation processes. So instead of having precompiled files, precompiled DLLs and so on, they just generate and compile code dynamically. And this, of course, has a lot of benefits. So let's analyze Havoc, the awesome Havoc framework, as an example. If we have a look at the code, we're going to see that the main agent of Havoc, which is the daemon, we're going to see that daemon exes and DLLs are generated directly from source code. Okay, this means that they don't use reflective DLL injection whatsoever. They are just code where all the settings are set and the code is built. That's it. But what happens when we want to generate a daemon cell code? What we will see is that the approach is quite similar to Metasploit, but with a builder. So, for example, the config settings are set dynamically before compiling anything, and this avoids the use of a configuration block and code to find it. And then the DLL, the daemon's DLL code is built along with the Cain loader component, which is an alternative to Stephen Feuer's reflective loader component. Okay, this is exactly similar. And finally, a little bootstrap code is prepended to the resulting DLL, which is once again in charge of calling the loaders export. So this is the code of the raw binary, the cell code. We see how, well, new builder, different settings, and finally DLL payload.build. The payload is built, and if it's successfully built, we get all the bytes. We read the payload as a buffer into DLL payload bytes. Depending on the architecture, we are going to find the bootstrap for x64 or for x88, the bootstrap, and we are going to prepend it to the resulting DLL. Okay? So more or less similar to Metasploit, but with some benefits, in my opinion. Very interesting. So yeah, as a final note about commercial tools. Yeah, commercial tools tend not to provide source code to avoid leaking capabilities to competitors or making analysis of their agents' tools harder. So yeah, we're probably not going to see dynamic code generation and compilation in commercial tools because they would be leaking all the source code of their really important tools. So yeah, just as a note. And the final section of this section, payload decorations. What I call payload decorations is the actions or modifications we do on a payload after we have generated it. The purpose is typically obfuscating it or removing bad charge or adding new capabilities to protect the payload. Okay. Note that these decorations, after we do these things, the whole payload will remain one single piece. It will remain a single independent code, position independent in nature. Okay. So yeah, it will be suitable for exploits, post-exploitation, and so on. Okay. So first example, Metasploit encoders. The main purpose of these is avoiding chars. Okay. There are some scenarios where specific chars are not allowed. So using an encoder always helps in those scenarios. So that's the main purpose. And Metasploit has a lot of encoders. But also encoding traditionally has been used as a layer of obfuscation. Well, nowadays it's not very useful. And yeah, if you use Metasploit encoders for evasion, you're not going to have good results. Trust me. And well, a final note, popular implementations do require read-write execute permissions because decoding the thing requires writing permissions and executing the thing requires execute permissions. So here I more or less explained the flow of how Metasploit encodes your payload and adds a decoder routine and so on. Okay, I'm not going to dig into this very much. Just I want to say that when you encode your payload, the result is going to be something like this. Payload, you encode it, you are going to receive your payload encoded, and then a decoder stub at the beginning of the code. And this works very similarly to what we have seen with the bootstrap and the reflective DLLs. When we execute position 0 of this cell code, we're going to execute the decoder stub. The decoder stub is going to decode the payload and is going to execute the payload afterwards. Okay. Another example, SGN Sikataganai. This one is in Golang and provides x64 support because the Metasploit one only supports x86. And well, it's very similar to the Metasploit ones, but has more stuff and is modern. So as you can see, we have the payload is encoded. There's a decoder stub or with some garbage. This is once again encoded, and then we have some garbage, a caller to the schema decoder, which is here below, and some garbage. So it's more obfuscated as the Metasploit ones. We also have something that Nighthawk provides, Nighthawk King. So Nighthawk provides a lot of ways to protect the payload and to make sure that it's only executed under the circumstances you have configured. So yeah, you can configure that the payload, the cell code, only executes when it can reach through DNS some domain, and it can read a specific string which is used to decrypt stuff. I'm not sure if it's used to decrypt, but I guess. And this is provided as additional cell code integrated with the agent's cell code. So is very cool. You can see DNS, HTTPS, DNS over HTTPS, user domain seed, registries. Is very complete, to be honest. Also, Cobalt Strike has the malleable PE, which are different settings to manipulate the beacon cell code after it has been generated. You can add, prepend, append, or replace data to the beacon DLL. And it's also quite nice. So if the export name of the beacon DLL is called beacon.dll, we can replace that name with another one. We can stomp specific strings with suspicious names and do a lot of these things. It's very, very, very complete. It also supports different obfuscation methods. For example, there is the obfuscate option, which is in charge of hiding or obfuscating the reflected DLLs import table. It encrypts and does different things to make it harder to analyze it. It removes unused things, and yeah, that's different stuff. Also, the Magic MC header, Magic MC options, which override the first bytes of the reflective DLL. We remember that when we saw, I have it here, I think. Yeah. MCAR are the first bytes. For the x64 are the default ones for beacon as well, I believe. So you can replace those bytes with other ones, but you need to make sure that they are valid assembly functions, assembly instructions, because this is, at the end of the day, a cell code, okay? We can't place anything, arbitrary things in this location, because we may break the bootstrap code. So yeah, that's it for the payload generation section. In the next one, we're going to start with analyzing and understanding the art of inserting payloads within executables. Again, thank you, and I hope you enjoyed. Bye.